Software testing is a fundamental activity in software development lifecycle, yet it is often misunderstood or underestimated, especially by new developers. This slide introduces the idea that testing is not simply about running a program to see whether it works, but also deliberately attempting to uncover faults, weaknesses, and unexpected behaviors. At this stage in your studies, you may associate success with writing code that compiles and produces correct looking output. However, from a professional software engineering perspective, a program that appears to work is not necessarily a correct or reliable program. Testing exists because software systems operate in complex environments and are used by humans in unpredictable ways. Even small programs can fail due to incorrect assumption, boundary condition, or misuse of data. The principles in this lecture are not tied to any specific programming language. Instead, they describe universal truth about how errors arise and how testing should be approached systematically. This lecture emphasizes that testing is a disciplined engineering activity. The principles you will learn here have been observed repeatedly in industry and research over decades of software development. By understanding these principles early, you will develop habits that scale from small classroom assignment to large real-world systems. Throughout this lecture, keep in mind that good testing is proactive, thoughtful, and intentional, not an afterthought added just before submission or deployment. The first principle of software testing states that a test case must include a precise definition of the expected output or result. A test case is not complete if it only specifies the input data without a clear expectation of what the correct output should be. There is no objective way to determine whether the program behaves correctly. That being said, the principle may appear obvious, yet it is one of the most frequently violated rules in practice. Students and professionals alike often run a program, look at the output, and decide that it looks right without comparing it against a formally defined expected result. This approach is dangerous because humans are very good at rationalizing incorrect output, especially when the output is very complex and large. Defining expected output forces the developer to think carefully about program requirements before execution. It also separates the act of testing from subjective judgment. In automated testing, this principle is essential because a testing framework can only determine success or failure by comparing actual output to expected output. In real-world systems, expected output may take many forms: numeric values, formatted text, database records, or system state changes. Regardless of form, the expected behavior must be clearly documented. Without this clarity, testing becomes guesswork rather than engineering. The second principle argues that programmers should avoid testing their own programs whenever possible. The core reason is human bias. A programmer knows what the program is supposed to do and is therefore more likely to overlook cases where it does something different. When reading output, the programmer's brain often sees what it expects to see rather than what is actually there. Another issue is emotional investment. After spending hours or days designing and coding a solution, it is psychologically difficult to adopt a destructive mindset. Testing requires you to assume that your program is flawed and to actively try to break it. The mindset conflicts with the constructive mindset used during this deployment. Additionally, if programmer misunderstood the program specification, the misunderstanding is likely to appear both in implementation and in the tests. As a result, the tests may confirm the programmer's incorrect assumptions rather than revealing them. In academic setting, the complete separation between developer and tester is not always feasible. However, this principle highlights the importance of peer review, code reviews, and independent testing whenever possible. Even a fresh set of eyes can dramatically increase the effectiveness of testing. This principle extends the previous idea from individuals to organizations. When a programming organization tests its own software, there is often pressure to meet deadlines and budgets. Time and costs are easy to measure, while reliability and correctness are difficult to quantify. As a result, testing may be viewed as an obstacle rather than a safeguard. Management may see extensive testing as a threat to schedules, especially when testing reveals defects that require rework. This creates an environment where testing is rushed, minimized, or treated as a formality. Independent testing teams help counter-treat this bias. This success is measured not by how quickly the software ships, but by how effectively defects are discovered before release. This separation encourages a culture where finding error is valued rather than discouraged. In professional software development, this principle underlines practices such as quality assurance department, third-party audits, and external penetration testing. While not always practical for small projects, the principle reinforces the idea that testing must be insulated from delivery pressure to be truly effective. Executing test cases is only half of the testing process. The other half is carefully examining the results of each test. This principle emphasizes that errors are often missed not because tests were poorly designed, but because test results were not analyzed carefully. Research has shown that even when incorrect behavior is visible in output, testers frequently fail to notice it. This can happen due to fatigue, information overload, or assumption that the system is functioning correctly. Once a tester believes a program is mostly correct, attention to detail often declines. Thorough inspection requires discipline. Testers must compare actual output against the expected output, not against intuition. This comparison should be systematic and, where possible, automated. Logs, assertions, and automated test reports exist precisely to support this principle. In practice, this principle encourages smaller, focused test cases with clear outcomes. When output is simple and expectations are explicit, errors are harder to miss. Careful inspection transforms testing from mechanical activity into an analytical one. There is a natural tendency to test programs only with valid and expected input values. However, many of the most serious software failures occur when programs encounter unexpected or invalid inputs. This principle states that effective testing must include both. Invalid input may include negative numbers, empty strings, extremely large values, or incorrect data types. Unexpected input may arise from user mistakes, malicious attacks, or integration with other systems that behave differently than anticipated. Testing these cases often reveals errors that remain hidden under normal conditions. In fact, test cases involving invalid or unexpected input frequently have a higher error detection rather than those involving valid inputs. From a design perspective, this principle reinforces the importance of input validation and defensive programming. Programs should fail gracefully, providing meaningful error messages rather than crashing or producing incorrect results. By actively testing abnormal conditions, developers gain confidence that their software is robust and resilient. Testing whether a program does what it's supposed to do is only part of the task. The other half is verifying that the program does not do what it is not supposed to do. This principle highlights the importance of checking the unintended side effects. A program may produce correct output while still causing serious problems elsewhere. For example, a payroll system might calculate salaries correctly but also modify unrelated records or generate duplicate transactions. Such behavior may go unnoticed unless explicitly tested. Unwanted behavior often involves side effects such as data corruption, security vulnerabilities, or performance degradation. These issues may not be visible in normal output but can have severe consequences in real systems. This principle encourages testers to think beyond functional correctness. Testing should also consider system state, resource uses, and interactions with external components. A truly correct program behaves correctly and only correctly. Throwaway test cases are those created informally and discarded after a single test run. While this approach may seem efficient, it leads to long-term problems. Whenever the program changes, the same test cases must be recreated, which is time-consuming and often avoided. As a result, errors introduced by modification may go undetected. This is especially dangerous in large systems where changes in one component can affect others. Saving test cases enables regression testing, which involves running existing tests after changes to ensure that previously working functionality still works. Regression testing is one of the most powerful tools for maintaining software quality over time. This principle encourages testers to treat test cases as valuable assets. Well-documented, reusable test cases reduce future effort and increase confidence in system stability. Unless the software itself is truly disposable, test cases should not be. Testing should never be planned under the assumption that no errors will be found. By definition, testing is the process of executing a program with the intent of finding errors. Assuming correctness undermines the entire purpose of testing. It is unrealistic to believe that any non-trivial program is completely error-free. Even after extensive testing and debugging, undiscovered defects almost certainly remain. Testing increases confidence but never guarantees perfection. This principle encourages a healthy mindset. Finding error is success, not failure. This principle states the probability of the existence of more error in a section of a program is proportional to the number of errors already found in the section. From the graph, we can see that number of errors found already is projected horizontally, where probability of the existence of additional errors are projected vertically. When number of errors found already increases, in proportion, probability of the existence of additional error also increases. So in the beginning, when we have very few or no error, there is chance that there should be very little or no error existence probability in the system. As we keep testing, we may find some defects or error in the software. In the long run, when the number of defects found in the system increases, then the probability of existing additional error also increases, and it goes proportionally with each other. For explaining the situation we described in our last slide, we can talk about an example. Suppose a program has two modules, A and B. In A, 5 errors have been found, and in B, only 1 error found. According to this principle, the likelihood of more error in A is greater than the likelihood of more errors in B. Errors tend to come in clusters. Some sections seem to be much more prone to error than other sections. If a module exhibits to be more prone to error, additional testing efforts should be focused on this module. As we are discussing about that example of finding error based on previously found errors in two different modules, let's talk in detail about that situation. If a program consists of two modules, classes or subroutines A and B, and 5 errors have been found in module A and only 1 error have been found in module B, and if module A has not been purposely subjected to a more rigorous test, then this principle tells us that likelihood of more errors in module A is greater than the likelihood of more errors in module B. Errors tend to come in clusters, and that in typical programs. Some sections seem to be much more prone to errors than other sections. The phenomenon is useful in that it gives us insight or feedback in the testing process. If a particular section of a program seems to be much more prone to errors than the other section, then the phenomenon tells us that in terms of yield on your testing investment, additional testing efforts are best focused against this error-prone section. This is the last principle of our slide. This principle actually describes that testing is an extremely creative and intellectually challenging task. There's been said that it sometimes takes more creativity and hard work to define test cases than developing a specific module. It is true that the creativity required in testing a large program exceeds the creativity required in designing that program. We already seen in previous lectures that test case designing can be done in a lot of different way. Then it is really hard to say that the program has been tested with 100% required test cases. um, that being said, it is quite impossible to perfectly test a system and making sure that system would never ever have a defect in future. Summary of this whole lecture is that testing is the process of executing a program with the intent of finding errors. The purpose of testing should always be finding errors, not trusting on the system. The mindset of the tester should be believing that the error and defect exists somewhere inside the system and they should find a way to figure that out. Testing is more successful when not performed by the developers, and developers should try to involve testers and other people in the organization to have an eye on their testing procedure or unit test development, or they can try to avoid testing their own code, instead forwarding it to other person in the team as well as forwarding it to a testing team for testing their whole software after being developed to a certain point. A good test case is one that has a high probability of detecting an undiscovered error. So the success of a test case highly relies on finding errors and defects. It does not depend on how fast or efficiently the test case runs. Successful test case always finds defects, and mostly it tries to find the undiscovered errors and exceptional cases. Successful test includes clearly and carefully defining expected output as well as input. Successful testing includes careful studying test cases and defining the testing scenario appropriately.